Okay, so we're going to go ahead and review for the midterm. Just want to let you guys know that how we are grading this. The midterm test can be very important to you. It can replace the lowest summative grade that you have. So it's a great way to bring up your average. Everyone has a great opportunity for that. Okay, so the first question we're being asked is how many atoms and how many of each atom make up one molecule of carbon dioxide. And so to solve this, you just need to look at the chemical formula for CO2. So CO2, every one of these letters is an elemental symbol. So you have two different elemental symbols. The number that comes afterwards, this little tiny number, is called a subscript. Now you can also have numbers that come in front. So if I had a 2CO2 like this, the number in front is called a coefficient. And the little number is called the subscript, and I would basically multiply those two together to get 4 if that were the case. But that is not my question. What is being asked is just a simple CO2 molecule, how many of each atom. So here, if you don't have a subscript, it's just 1. So I'm just going to go ahead and make a little table to list my atoms. I have 1 carbon, and then for oxygen, I have a subscript of 2, so I have 2 oxygen. So my answer here would be 1 carbon and 2 oxygen. If you listen to the name, it can kind of give it away. In science, di means 2, so carbon dioxide means 1 carbon and 2 oxygen. So the name kind of gives it away. Going to your next. What does the law of conservation of mass state? And that law states that energy is never created nor destroyed. That's actually wrong. That's actually the law of conservation of energy. But you could say matter is never created nor destroyed. Okay, so the first one that I have up here, this one's the law of conservation of matter. The second one's the law of conservation of energy. Be aware of both of them. They're the same thing. You just switch out the words matter and energy to find the answer there. Okay, next question. What energy conversions take place with photosynthesis? So the first thing we have is we have light energy, sometimes referred to as electromagnetic energy. And that is going through a process where it is using chemical energy. So it is converting that light into what we know as chemical energy. Now it's a little bit more complicated than that. You could say that inside the sun you have nuclear, and the nuclear energy is giving off light. Then that light energy is going through a type of chemical process. There's chemical energy involved, which creates another kind of chemical energy. But let's just say light is being converted into chemical energy. That I think is fine for you guys at this level, but just understand that for those of you who want more, that there's actually more involved there in that scenario than just that simple conversion. Okay, next question. If you mix 32 grams of salt with 45 grams of water, how much salt water will you have? Well, guys, this goes back to the law of conservation of mass. And to solve this, you simply take 32 grams and you're going to add 45 grams. So 2 plus 5 is 7, and then 3 plus 4 is 7. So you're going to have a total mass of 77 grams of salt water. Now this again is going back to the law of conservation of mass, in that what it is saying basically is that all matter has to be accounted for. You can't just have matter disappear or be lost or created out of thin air. Every gram of mass must be accounted for in your questions here. All right, next question. I think this is number 5 on your study guide. What happens to the speed of particles as energy is added and temperature increases? Well, the speed is going to increase because what's happening there is the kinetic energy increases. Therefore, speed increases. Okay, so that's what's occurring there. Remember your formula for kinetic energy. Kinetic energy is equal to 1/2 mass velocity squared. I'm going to pause for a brief second while you write that down. All right, next question. How do the speeds of particles in a solid, liquid, and gas differ? Well, solid, they are extremely slow. They kind of hold their place and just simply vibrate where they are. They do not really move too quickly at all. Sorry, I need to rewrite that. So they vibrate in place. In a liquid, they are moving a bit faster. And then in a gas, they are moving the fastest of all. Now, it is because of this speed that what you'll actually see is the amount of volume change. So in a solid, your volume is pretty tight. It is they're compressed, they're together. In a liquid, it spreads out a bit, and in a gas, it spreads out more to accommodate that speed, that high velocity. So guys, as you add energy, as you add temperature, as you add energy to something, as thermal energy increases, so does the kinetic energy, so does the speed. It's all connected. Okay, so it is if you wanted to graph that out, you would see a 1-to-1 correlation and a positive slope, where one of these variables would be the temperature, one of these variables would be the speed. Okay, so just understand that those kind of go hand in hand. Okay, what is the state change from a solid to a liquid? Well, that is known as melting. Okay, so melting is going to be a solid to a liquid. The opposite of that, I went from a liquid to a solid, is known as freezing. They occur at the same temperature. It's just whether or not you're adding energy or you're removing energy to something, to a material. Okay, what is the state change from a liquid to a gas? From a liquid to a gas, that is known as evaporation. Evaporation. You can actually see the word vapor in there, and the word vapor is another name for gas. State change from a solid to a gas. So again, guys, you're going from a solid directly into a gas. You're skipping liquid altogether. Now, you're not going to see this happen most of the time. The only thing you're going to see it happen to is dry ice, and we really cannot bring that into school because it's just too dangerous. But that process is known as sublimation. And again, it's a state change from solid to gas. It skips the liquid phase altogether. If I go from a gas to a solid, again, it's the same thing I just showed you, but I'm going from a gas to a solid. This is not one that you're very familiar with. This does not happen on Earth except in laboratories. It does happen on the planet Mars when you have CO2 that freezes, but this process is known as deposition. deposition. So, from a liquid to a solid, I just previously told you this, but let's go over it again. If I go from a liquid to a solid, that is the opposite of melting, and that is known as freezing. From a liquid to a solid, that is freezing. So again, you start out with that liquid, it gets cold outside, and then next thing you know, you have that ice cube that is formed. This is happening right now in the mornings when you have ice on your car, or your parents have ice on their car, rather. The difference between a physical change and a chemical change. This is important to know, to be able to distinguish between these two. So, a physical change is going to be a change in physical properties. It's a change in physical properties. Okay? A chemical change is going to be a formation of new substance. Okay, and just to kind of illustrate these points here, if I take water and I freeze it into ice, then it's still going to be H2O. It started out as H2O, it's still H2O. By contrast, if I have a log of wood and then I'll light that log of wood on fire, well, it's going to change into something totally new. I'm just going to have some black ash left over, mostly carbon. And so I'll have a new substance. I won't have what I started out with. I'll have something totally different. And so I'm going to give you guys just a second to make sure that you have that. Okay, what is an example of a physical change? Well, guys, I just gave you one. Let's give you another one. Like I took the ice and I made it from the water. Another example would be like if you had a sheet of paper and you took that sheet of paper and you just tore it into two pieces. That is going to be a physical change because that is a change in the size of something. It is still paper, but it has a different shape and size. And things like shape, size, color, those things are just physical properties. So that's my example. Feel free to make up your own example. But again, a physical change is going to be a change in physical properties. Example of a chemical change. I gave you one earlier, but let's have a different one, okay? Again, all chemical reactions. So every time you have a chemical change, it's going to require a chemical reaction. If you mix, let's say you have some vinegar, and then you have some baking soda, and you pour it on top, it's going to make a bunch of bubbles, okay? That's going to release CO2. Well, that CO2 was not present before. You did have the oxygen that was kind of like locked into place here, You did have some carbon that was locked into place here. And when you combine the two, you see all these bubbles form. A reaction takes place, and it releases that CO2 gas. We demonstrated something in our classroom. We went outside, and we had a bottle of Diet Coke, and then we also had some Mentos. We put the two together, and then we had this massive explosion that kind of like went just the Diet Coke went up in the air like really high. So Mentos and Diet Coke is another example of that. You could also write down vinegar and baking soda. There's many other ones you could think of, like burning a log is a great example. If we have a sheet of paper and we tear it in half, that's just going to be a physical change. But if we actually take that paper and we were to burn it and just light it on fire, well, that's going to be a chemical change. So all chemical reactions are chemical changes. You cannot have one without the other. Oxygen reacts with iron to produce rust. How is rust different from iron? Well, they have different chemical and physical properties. The truth is iron, and iron oxide is iron oxide. So whereas iron will react with oxygen, iron oxide will not, because it's no longer reactive. Iron is pretty reactive, but iron oxide is not. It's already had that reaction. So the idea is once you have that chemical reaction, you no longer have the same thing you started with. You have a different substance with different properties, chemical and physical properties. All right, what are physical properties? These are observable characteristics. Just to give you some examples, we have size, state, whether it's solid, liquid, or gas, color, mass, texture, ductility, malleability, all those we mentioned earlier in the school year, but those are all going to be physical properties. These are things you can observe without having to change the substance. Physical properties, I just gave you those examples. Let's write them again. Size, color, volume. Volume is the same thing as size. Mass, state, all of those things. Again, easily observed. Just did that one right here. Chemical properties. So these are a little bit different here, guys. We have flammability. One that is very much like flammability is combustibility. And you cannot observe these unless you're having an actual reaction take place. Reactivity. These are three great examples. These are the three most prominent examples. You could also say if something's an acid, so you could say acidity, alkalinity. That's getting a little complicated there, but those are the three big ones I want you guys to know. Okay, flammability, combustibility, reactivity. You can only observe those during. What is the mass of a lithium atom? So lithium is number 3 on the periodic table. And if you look below that number 3, you're going to see a number down below. I believe it is 6 point something, 6.9 something. Okay, so we're going to round that to a 7. So we'll say the mass is 7 AMUs. Now what this means is if it's close to 7, we're going to, like I said, we're rounding this. You know that it has 7 things inside that nucleus of the atom, not the electrons. The electrons are really tiny. We don't worry about them. They float around the outside. But in that nucleus of the atom, we have 7 things. 3 are protons. That means the other 4 have to be neutrons. What does the atomic number represent? That would be the number of protons. These are those positively charged particles. Every different element has a different atomic number. Carbon is 6, oxygen is 8, nitrogen is 7, chlorine is 17, hydrogen is 1, and so forth. How many neutrons are present in a carbon atom? So if you look at carbon on the periodic table, it's got something like this. It has an atomic number 6. The atomic mass is something like 12 something. So in carbon 12, or carbon, again, you have number 12 down here. So 12, you're going to subtract that atomic number, which leaves you with 6. So it's going to have 6 neutrons because the atomic mass at the bottom here minus the atomic number equals 6. That's how you get 6 neutrons. An atom has 10 protons. What is it? It would be neon, because neon's atomic number is 10. It is that simple. It is that simple. Moving along, what is a compound? A compound is a substance formed by 2 different elements, comma, chemically bonded. Remember, if they're not chemically bonded, it's just a mixture. Just a mixture. So again, 2 different elements chemically bonded. What is a particle of a compound? Those are called molecules. Now, do not be deceived. If I have oxygen gas, that is also a molecule, but it is not a compound because it is the same element. In order to be a compound, you have to have 2 different elements. But all compounds, a particle of a compound is known as a molecule. 3 examples of compounds. Well, we have sodium chloride, which is table salt. We have dihydrogen monoxide, which is water. We have carbon dioxide, which is the gas you breathe. We also have methane gas, which is present on any planet that has life. Those are just some great examples of these different compounds that you're around all the time. But guess what? Oxygen gas, not a compound because it's only one element. Where is most of the mass of an atom located? That is in the nucleus. This is also how we get nuclear energy, from the nucleus of atoms. What is a pure substance? It is defined as having only one type of particle. Now, there are 2 types of pure substances. There is going to be element, and there's also going to be compound. So these are the 2 types of pure substances. Some examples of pure substances, we can say oxygen. Oops, I can't see that. Say oxygen, carbon dioxide, water, salt, nitrogen. A non-example, so if I wanted to give you a non-example, I could say salt water. Salt water is not a pure substance. It is a mixture. So remember that all mixtures are not pure. Everything that exists is either a pure substance or a mixture. But that's my non-example, but all of these are great examples, and you guys need to have your own for this question. You can take some of my examples, but I want you to get your own too. Next question, 3 examples of conductors, 3 examples of insulators. Let's do the insulators first. They are much easier. So insulators, we have plastic, wood, and let's go with rubber. Those three things will not conduct heat. They will also not conduct electricity. Some great conductors are aluminum, iron, and gold. Those are some great conductors. As a matter of fact, gold is like one of the best conductors of electricity. My favorite metal is, strangely enough, it is copper. I love copper. I love the way it looks. I think it's really cool. And I love copper cookware. It's really cool. All right, last question. Oh, look, it's a bonus question. So, create a Bohr model of oxygen. Let's go ahead and let's do that right now together because I love Bohr models. Okay, so first of all, we draw the nucleus. Go ahead, draw your nucleus. You can draw your nucleus right now. All right, in that nucleus, you're going to write down 8p for 8 protons and 8n for 8 neutrons. Now, for me, I put like a little plus symbol and a little 0 symbol. Oxygen, if you look on the periodic table, draw your quick periodic table. There we go. That's the ugliest periodic table that ever was made. We find oxygen right here. It is in group 16. That means it has 6 valence electrons. It is in period 2. So that means it's going to have 2 electron clouds. So we have 6 valence electrons and 2 electron clouds. So the first circle can only hold 2. First circle can only hold 2. And this outside circle is going to hold 6 because I'm in group 16. We have to spread out our electrons. I do want to remind you that a Bohr model is not an accurate representation of what it actually looks like. It's just a quick way to make it so we understand it. And so that is the end of your study guide. Please make sure you study for your midterm. Please get a good grade on your midterm. It will definitely help your average in class.